So here's a problem in case you need it. So let's move on to the solution. So what we're trying to find is the electric field at point P. So judging from the configuration that we have, you can expect the electric field to have a vertical component that points in the y direction, and then a negative x component that points leftwards. So with this in mind, we can actually, in order to find the electric field at point P, we're going to have to find that these two components, the vertical component in the y direction, and the x component in the horizontal direction. So let's try to find this one first, EY. So how do we find this? So in order to find the electric field, I'm going to have to define this angle theta over here, and then this length x. So this length, this x is going to be our variable, so it's going to move along this line. So that makes our integral something from 0 to L when it's defined in terms of x. So what exactly do we have to integrate? So I have to find this theta here, and it's going to come in useful later. So going back to the integral, we're going to have our Coulomb's law. So we're going to have to multiply it by the charge. So the charge is going to be the charge density times dx, right? We're using x over here as our variable, so we're going to integrate it in terms of dx. And then we're going to have to divide this with respect to the distance squared. So the distance is x squared plus z squared for square root. So the distance squared is just going to be x squared plus z squared. And then since at this point we're trying to find the vertical component, you can see that for this point charge here, we're going to have an electric field that points somewhere in this direction. And then you can see that we can actually split this up into the vertical and horizontal components. So let me just get rid of the p to draw this better. So the electric field is going to point somewhere in this direction. And we can actually break this up into the x and y components. And then using a bit of geometry, you can see that this angle here is also theta, this small angle here. So the vertical component is just going to be this whole thing over here times the sine theta. And then since we're doing everything in terms of x, we're going to have to define sine theta in terms of x as well. So using this triangle that we have here, this triangle, we're going to see that sine theta is going to be equal to z divided by x squared plus z squared, using Pythagoras theorem. So you see that this diagonal line is going to have a length of x squared plus z squared. So essentially there we have it. We have our integral. So the rest of the steps that we need to do is just math. So let me just rewrite the integral that we need to deal with. So 0 to L, 1 over x squared plus z squared, 3 over 2 dx. So how do we solve this integral? So let me just rewrite what we have. So we had a lambda, the charge density, and then we have this integral. So the trick to solving this integral is using substitution. And the thing that we're going to substitute is that we're going to let x equal to z tangent theta. And the reason for that is that it's going to get rid of this denominator here, using the fact that 1 plus tangent squared theta is going to be equal to secant squared theta. You can prove this using the identity sine squared theta plus cosine of squared theta equal to 1. So using this, you can prove this. Just divide both sides by cosine squared theta. So doing our substitution, dx, what's dx going to be? Dx is going to be equal to z secant squared theta d theta. So in case you don't know, the derivative of tangent theta is secant squared theta. So for dx, we're going to change that to z secant squared d theta. And for the denominator, x squared is going to be equal to c squared tangent squared theta. So we're going to have z squared 1 plus tangent squared theta, 3 over 2. And then for the bounds, for 0, tangent 0 is equal to 0, so we go from 0. And then for the time being, I'm going to put down alpha. So I don't know exactly what this value is going to be. All I know is that for our present case, L is going to be equal to z tangent alpha. So that's the definition of how you translate the bounds. So I'm not exactly sure what this alpha is going to be. Well, you can write it as as something like this. So yeah, so this is what our alpha is going to be. So I have no specific value for this, so it's just going to be this expression. So instead of writing this gigantic expression we have here, I'm just going to use alpha for the time being. And so cleaning up the expression that we have, secant squared theta d theta. So let's observe what we have in the denominator. So for a z squared, it's going to go through a power of 3 over 2, so that we're going to end up with a z to the power of 3. So for the 1 plus tangent squared theta, we're going to change this into a secant squared theta. And then since it undergoes a power of 3 over 2, it's going to turn into secant theta to the power of 3. So I see that we have 2 z's over here, so these cancel out. We also have 2 secants here, so these cancel out. So all we're left with is going to be 1 over 4 pi epsilon divided by lambda over z with an integral from 0 to alpha 1 over secant theta d theta. And so carrying on, so this is what we have for the time being. So how do we solve this integral? So notice that secant theta is actually just 1 over cosine of theta. So 1 over secant theta is just going to be cosine of theta. And this is definitely something we know how to integrate. So in the end, we get sine theta 0 to alpha. So sine alpha is just going to be sine alpha. And then sine 0 is going to be 0. So this is what we get. So in order to get rid of the alpha, we can look back at our expression. We know that tangent alpha is going to be equal to L over z. So we can actually see that this alpha corresponds to this triangle over here. So L and z. So in that case, sine alpha is going to be L divided by this length, which is L squared plus z squared. So in that case, we're going to get this expression, L over z squared plus L squared. So this is going to be our electric field in the y direction.